I will now start describing you in more detail some of the clustering learning code. This code is available on clustering learning paper 1 code on GitHub under my name. And this is really the address, and this is the code for the paper that we just discussed. So I will actually show you a slightly different version of the code it's called basically I call it Train Berkeley. It's very similar. It runs on a slightly different data set, but the whole idea remains about the same. So this code will do the following. For example, first of all, we load all the variables that we need to load, and we load a data set. In case of the clustering learning paper, we load other data sets like street view house number or CFAR 10. We also set up some parameters. More importantly, I set the number of threads to be as many as my processor has a number of cores. So if you have 4 or 8 cores, you can set the appropriate number of threads. In my case, I have 4 cores, each one with 2 threads, so it should be capable of 8 threads. We also, the input size of patches that I'm trying to learn, image patches, are 7 by 7. And then I want the 16 filters in the first layer. Don't worry about second and third layer here. These are just for a slight different application. For now, I will just show you the code to train a 7 by 7 patch on this data set, the Berkeley data set, which basically has 56 by 56 local contrast normalized patches of images, of which we just take random 7 by 7 patches to learn 16 filters with the k-means algorithm. Other parameters are a number of iteration of k-means, which here is set to 15 just to make it fairly quick. The patch size, so how many inner loop of k-means, how big the matrix you want it to be. So 1000 is usually a good value. Number of samples, random training samples. And then the standard deviation for the initial sample of k-means should be 0.1. We set the number of threads, and then we set the default tensor to float. And we don't really need a double precision. Otherwise, you're gonna just increase this capacity of your network by numerical precision, not exactly by neuron capacity. In fact, in many cases, I would like to have not even a 32-bit, but more of a 16-bit resolution here, or even lower, just to test what's the pure capacity of the network and the connection, not of individual neuron capacity. So we set up some shortcuts. So the size of the patch that I want to learn, I call it IS, and the size of the number of kernel that I want to learn is NK1. Forget about the other 2 layers for now. We also set up a Gaussian filter just for other operation, level normalization. So first of all, what we do is we basically process the data set. So we just load the data set, basically, which is just a large number of images. And I just want to have I just want to try to get 256 of these images. And then I basically set up a variable called train data, similar to what is done in the tutorials by Clément Faravé. And this data is a torch tensor of 256 free planes and of the size of the data set. So in this case, it's probably 56 by 56. And then what I do is I basically load the data set that I previously loaded, and I load the images, and I just copy, since there's free planes here, and for simplicity I wanted to keep free planes to keep it conforming to other data sets. I just copy the same data on all the free planes, but it's basically just the free data. So imagine it's really a black and white image, but here I'm copying the same value to the free channels RGB. So it really doesn't really do anything. And then I show, I take just one 256 example of the image and of the same input images, and I display them. And I verify the statistic of the data that I want the data to have zero mean and a standard deviation of approximately 1. Then what I do is now I sample, I basically generate the first layer filters and I extract all the patches that I wanted. So what I do is I basically take a random image from the data set, just one of the random images, and I basically take a patch as big as IS. So I take a coordinate IS. I take a coordinate of this a random coordinate of this image that is from 1 to IS minus 1. And then I take a random patch here. So I take a patch that is big, basically IS, is as large as IS by IS, so 7 by 7 in this case. And then I remove the mean to that patch, just because the images could be more globally normalized, and I actually want to have my patch with zero means as much as possible to run the k-means algorithm. Then I can show a few patches just to make sure that I'm getting the right thing. And then I run the k-means algorithm. So there's a callback function which displays the kernels as they get learned at every step. And then this line just runs the unsup k-means algorithm. So this is a supervised package in Torch that you need to load. You find it on GitHub, like any other package of Torch. And you pass him basically the data, so these random patches. And I want NK1 kernels with the optional, the standard deviation that I set, the thousands matrix size in the iteration that I want, and the patch size I want, and then the callback function to show periodically what I'm learning. And then you just run this thing, and you can clean up filters. Some of them are returned and it's not a number. There was previously a bug in k-means, but it has been since fixed. Then usually I normalize the kernel that I learn. Each one of them I try to I remove the mean and divide by the standard deviation, so that I basically have perfect training samples. And then I just show the first layer filters. So this is more or less the code that I wanted to describe to you guys, and then now I will just run it. I will just run torch train berkeley.lua so that you can see what happens. So what happens is these are the input images. So these are patches of the input images that 56 by 56 local contrast normalized that I use. These are the patches for learning. So there are 7 by 7 patches picked at random from those images. And these are the filters that I learn after 15 steps of k-means. It's basically as simple as k-means gets. This is the clustering learning algorithm that basically takes a bunch of patches and allows you to learn filters. So basically the base function that you need. It's as simple as that. This technique is quite simple and effective, and I really recommend people to try to use it. One final comment that I wanted to make today is that in some of our tests, and in particular in our paper of clustering learning, we show that you can actually get some pretty good performance even with random filters. So that's a bummer, because if you have a training technique, it's unsupervised, you would want it to do better than random. But there's a paper, actually, a recent paper, was pointed to be by Adam Coates from his group, Andrew Sachs, that looked at why random weights and supervised feature learning work as well. So I wanted to share with you, and the main idea is that when you use a standard convolutional network like us, so you have a pooling, a convolution, then a next input layer, then what happens is that if you compute the optimal basically the optimal filter for a convolution, when you have random filters, so the optimal input for this kind of filters that you can do basically by trying to look at sending random patches to that specific convolver, and looking at this output and do a weighted average of the input and the outputs multiplied together, and you can compute sort of the best patch that this is selective for, and you sort of get some kind of a Gabor, not really Gabor, a combination of Gabor, so they're kind of like combination of sinusoidal lines. So they're very frequency selective and orientation selective, as you can see, and they're quite similar to the filters that you could potentially obtain. So in this paper, they basically propose tell you that sometimes it's much better to just initialize your network and with supervised weights and with the random weights and check its performance, because they did some tests and they show that basically random weights gets you very close to the actual best performance anyway. So you might as well try random weights first before you venture into training. So this is quite an interesting paper, and in a debated topic of deep learning, that tells you basically that sometimes training too much with especially complicated technique might not get you much better than a random filter, which is a bummer. It might mean that, like a discussion that I had with Clément Farabet, might mean that actually the information that really filters give you is not that high. What really can give you selectivity and information is how to set up this network. Or it might just mean that having a large number of these filters and multiple layer will do just as great as anything. So this is a debate and something that needs to be more studied. In particular, we're going to try to study this in the context of clustering learning to see, does it really make sense to cluster things or do some other training, or does it really, or do random weight really work as well? Also, the distribution of the random weight really matters. So these debates will be probably go on for a while, so I recommend you to look at the scientific literature in the next few months or weeks or years.